The purpose of this lab is to analyze the motion of a spring mass swinging in an arc while oscillating due to a spring. Here we are using Newton's second law and the energy principle to compare the data from Tracker to the computational model. Here we have the Tracker video I used in order to analyze the data. First of all, I set my origin at the beginning of the spring, and I used the calibration stick starting from the origin to the end of the spring. I found this to be 0.7 meters. Now, after we know our initial data, we can now analyze the video. After we have found all the center points, and after the video is ran, we get graphs on the right here. Now, these are all the data points of the x's and y's of our video. Now we can use this, we can apply these data points into our new Newton's second law and energy principles. These will be used in order to compute a computational model. Now that we have analyzed the data, we can now apply these formulas. First, we have Newton's second law. We've already gone through this in previous labs, but here we're using it again. This is a fundamental principle. We see that F net is equal to mass times the change in velocity over delta t. Now here the F net is equal to all the forces on the system. And for our video, we're using the force of gravity and a spring force. When we add these two together, this is the total net force. I've also manipulated this formula to show that the velocity final is equal to velocity initial plus the F net divided by m times delta t. Here's another formula that we will need. This is the energy principle. And the energy principle states that the total amount of energy is equal to the change in kinetic energy plus the change in potential energy of gravity plus change in potential energy of the spring. And this will all equal out to 0. This is 0 because this is stating that no energy will be created or destroyed. Here we see that K, or kinetic energy, is equal to 1/2 mass times velocity squared. Gravitational potential energy is equal to mgh, or mass times gravity times height. And spring potential is equal to 1/2 ks x squared, where x is equal to the length of the spring minus the relaxed length. And ks is the spring constant. Before we can write our code, we need to know some initial calculations. First of all, we need to know the period between each oscillation. From the video, I found that for every 3 oscillations, there was a time of 4.3 seconds. So, for each oscillation there's a time of 1.45 seconds. And from here, we can find the spring stiffness from this equation. 4 pi squared times mass divided by t squared. And we just found t, so we can plug in. When we plug this in, we find the spring stiffness to be 5.86 newtons per meter. Now from here, we can find the relaxed length of the spring. We already know what the length of the spring is. We found it was 0.7. So we plug that in, and we subtract the mass times gravity divided by the spring stiffness. When we do that, we get the relaxed length to be 0.12 meters. Now we are able to write the code. Here I filled out the code. As you can see here, we have F grav, F spring, F net, ball velocity, and ball position. We have found all of these using Newton's second law and the energy principle. For F grav, it is simply the ball's mass times the gravitational constant. And this is a vector because it's pointing in the negative y direction. F spring, as we said, was negative ks times s times L hat. Here L hat is the direction of the length minus the relaxed length of the spring. And the F net is the force of the spring plus the force of gravity. Now, we also need to know K, as we stated from the energy principle. And this is 1/2 times the ball's mass times magnitude of the ball's velocity squared. And delta K is the final K minus the initial K. Potential gravity, as we said, the ball's mass times gravity times the ball's position. The delta U is simply the final potential gravity times the initial potential gravity. After we run the code, we get something that looks like this. Here we have the different energies of our data. The total energy is here in yellow, which is 0, which is what I said earlier. The green is the gravitational potential, the blue is the kinetic, and the red is the spring. You can also see in the model that the blue is the computational model, and the red ball is the data that we got from Tracker. And as you can see, it's not perfect, but there are some similarities. So what does it mean? For your model system, is the energy principle satisfied? As you can see from the model, the yellow line indicates the total energy. And this should be 0, which is what we see here. And this is good, because that means there's no change in energy. That means no energy is coming in, no energy is going out. We can also see here that the gravitational potential energy is in green, and the kinetic energy is in red. And as the kinetic energy increases, gravitational potential decreases. And this is true. And based off this, we can say that the energy principle is satisfied. So what if? Using the data you obtained in Tracker, make 2 separate estimates of oscillation periods. Estimate the X position data and the Y position data, and compare these two. So as we look at my graph, we compare the X and Y position data. And after I analyzed this, I found the time to be about 1.58 for the X and 1.6 for the Y oscillations. And when we analyze this, we figure out that the spring is spending more time oscillating in the Y direction than the X direction.